it turns out that I actually can't confirm or deny this story, okay? I can't say. But here's the situation. An alien falls to Earth. It was kind of like an asteroid sort of thing. It kind of cracked open. There's this little alien in there. But in Earth's ideal environment, it starts to multiply. Okay? It starts to multiply. It starts to spread. And it doubles every hour. It doubles itself every hour. So the question is, and the issue is that it's actually toxic. It kind of gives off this toxic gas. It was in a rural area. People won't be able to get to it to neutralize it for 24 hours. So the question is, how many aliens will there be after 24 hours? So take a moment to kind of think about it. You've got a calculator. You might be able to figure it out. So the situation is one alien, right? What does it do every hour? Doubles itself every hour. And we're wanting to know how many aliens in 24 hours. So think about that for a second while I take roll. 48. Yeah.
Probably, maybe not. 24 times 2. It's probably not right.
16 times 16 is 4.
Anybody got an idea?
48.
48? Maybe 48 aliens?
Or maybe 24. Oh, wait,
Maybe 48, yeah.
Actually, but that would be.
I think I know. I
Because
think
that'd be one each hour. Or 2 each
I
hour.
think I got the.
Okay, so there's a guess of 48.
I got 576.
576.
Oh, that sounds more reasonable though.
You think so?
Oh, wait,
576.
isn't it 24 times 24?
24 hours.
Maybe, yeah.
Anybody else got a venture a guess? What do you say? Oh, anybody?
I'm sorry.
No? Oh, you're good? Okay. All right. Well, let's kind of think about how we could maybe figure this out. So I got you this table right here. Let's think about what if there's kind of a pattern to it, because I think if we can get the pattern, we'll have better luck. Oh, that's frozen, isn't it? We'll have better luck figuring out the 24 hours. At time 0, when it first lands, how many aliens do we have?
1.
We got 1, don't we? That's the starting time. So at the 0 hour, we've got 1 aliens. But then an hour goes by, and then pop, how many aliens do we have?
2.
We got 2. So you kind of have this picture here, don't you? Do you see how it's like, 1 alien, but then it spreads, but then the next hour, doesn't each of those aliens also split? So how many do you have after 2 hours?
4.
You have 4. After 3 hours, if those all split, how many do you have?
8.
You have 8. And then 4 hours, 16, and 5, 32. Okay? So after 5 hours, we're already up to 32. So what do you think, River? You think 48?
Probably not.
Probably not. I think we're going to pass that pretty quick. Oh, actually, 1 more hour, we're past it, aren't we? At 1 more hour, we're at what? 64. Yeah, so this is growing pretty good. Well, it turns out, do you guys want to know how many aliens there will be, or do you want to tinker with it some more to try to figure it out? So it turns out there are going to be 16,777,216.
I got that.
You got it? Yeah? Okay. There's going to be that many aliens at the end of 24 hours.
So 2 times Oh, so 2 to the 24th power, right?
So what did you do? What did you do, Addie, to figure that out?
I just multiplied it a bunch.
So you did, you just started
just did
multiplying
it
by
every
2,
time.
and then you luckily
I got a
didn't
2.
mess up and do 1 too many or 1 too
Yeah.
less. You kept good track. Yeah.
I don't know how to do the 24th power.
Okay, so here's the thing. You multiplied 2 24 times, right? Can we think of that as an exponential situation? So a shortcut for that, a shortcut for doing all that multiplication is to say, oh, well, you've got, okay, maybe I'll write it up here. You've got 1 alien. We're going to multiply it by 2, but how many times are we going to multiply it by 2? 24 times. So is that something that's going to be a little easier to enter into our calculator?
Mm-hmm.
Yeah. So and I'll just give you a heads up. What we're gonna do is realize that this is kind of like a formula we can use, where this number is the starting amount. And we'll explore this more tomorrow, but you've got a starting amount. And then this 2, that was how much it was multiplying each time, right? We call that a growth factor. A growth factor. And so we can actually use this sort of relationship on a lot of different shapes, or a lot of different situations, I should say. So, and also we're going to graph these soon. But yeah, it turns out when we graph these, we're going to be looking at, when we write equations for them, the equation is going to be like this. It's going to be y, the result is y. Y is equal to, and in this specific case, there was one of them times 2, and then we could write a formula for this. Put an x up here, because now could we figure out how many aliens there are for any hour? You know what I mean? We could find out how many aliens there are after like 3 days, which would be how many hours? 72, wouldn't it? We could put a 72 in there. Maybe a week, you know what I mean? Multiply all that out, and that's going to be a pretty big number right here, isn't it? Imagine what a big number here is going to do to this answer here. It's going to be massive, isn't it? So in our particular case, we ended up with 1 times 2 to the 24, which would get us that answer right there. Well, it says the alien is an example of an exponential function, and exponential functions multiply, and it turns out they also could divide at each interval. Linear functions, which we've already studied, they add or subtract at each interval. So take a look, if you would, at a linear example versus an exponential example. See how across the top, as we go to the right, what are the x values doing? They're adding 1, right? But then look at how the y values are increasing. How are the y values increasing as we go from left to right? They're adding 3. And what we've learned is that if you take the amount the y is rising and divide it by the amount the x is rising, that gets you slope. And you can write an equation for these. You can go y equals mx plus b, and it turns out that the slope is this number right here. It's going to be 3. And then what was your starting amount? Your y-intercept, yeah, is right there. Your y-intercept, or your starting amount, is 2. So yep, there's the m, there's the b, and you can write an equation using y equals mx plus b for linear relationships. Well, for exponentials, what are the x's increasing by? In this case, it's increasing by 1 each time again, right? But then, what kind of pattern is it for the y's? Yeah, it's multiplying by 3. Now, it's kind of hard to tell by looking at the fractions sometimes. I can usually tell right here. See how this fraction is becoming a 2? What did they have to multiply to go from 2/3 to 2? 2/3 to 2. Wouldn't they have to multiply by 3 to undo it? Or multiply by 3 to go from 2 to 6, from 6 to 18. So they are multiplying by 3. And that's how you know it's exponential. Linears add, exponential relationships multiply. Okay, they multiply. Now here's the format for exponentials, and I don't know that it has a definite name. This is kind of the most basic exponential function that you can write, but it goes y equals a times b to the x. And a is going to be the y-intercept. It's going to be the starting amount. And b is going to be your growth factor, how much it's growing. So what's b going to be? 3. And you can write it out. Y equals 2. You start out with 2, your y-intercept, your starting amount, times 3 to the x. And that is an exponential model. What do you guys think? So it's linear if you're adding at each interval. It is exponential if you're what? Multiplying at each interval. So just to verify, up here, and by the way, up top, you should, to make it easy, they'll almost always go by 1 across the top, just to make everything easy to calculate. But as long as they're going by 1 interval up top, you can easily judge what the growth amount is going to be or what the slope's going to be. But do you guys see how the pattern here was multiplying by 2 for each step? Timesing by 2. So that's how we were able to get an equation for that. Okay, part of what you're going to be responsible for in 6.3 is determining whether or not something is exponential or not. So let's practice that a little bit. We'll just write out a few equations here, and I want you to decide if it's exponential, or I guess it could be linear or some other type, but we're just curious if it's exponential or not. So if I have y is equal to -2 parentheses 3 exponent of x, is that exponential or not? It's totally exponential, isn't it? It is exponential because of that guy right there. Exponential. What about y equals 5x? Is that exponential?
Linear.
That's linear, isn't it? That one happens to be linear. And y equals, and this one's kind of tricky, 7 -2 in parentheses to the x. My gut tells me that this is what? Exponential. But it turns out these b values, the growth factors, Does it make sense that it's growing by multiplying by a -2? Think about what that would do. If you were growing by a -2, wouldn't you flip-flop between negative and positive at each interval? You know what I mean? If you started out with one thing, well, then an hour later you'd have -2 things. And then an hour after that, you'd have +4 things. So it turns out that to be exponential, it can't be negative. The growth factor can't be negative. So just kind of keep that in mind. I don't think that comes up very often. We're more concerned about telling the difference between these two. But yeah, it turns out this one is not exponential. I don't even know what you'd call it.
So it's not linear either.
It's not linear either. Yeah, if you were to graph it, it's kind of cool. You don't have to write this down, but if you were to graph it, it would look something like this. You'd start out at like 1 or whatever, and then you'd go to -2, then you'd go to +4, then you'd go to -8, and it would just kind of do this zigzag, or I don't know what you'd call this. And actually, that's probably not accurate. That's kind of looking like a absolute value graph on its side, but it would actually be more kind of like a anybody in band? Kind of like a flute or a trumpet. You know what I mean? Is that called the bell? Is anybody in band in here? Yeah, is that called the bell? The part that kind of flutes out?
I think so. I'm not brass.
Okay, I got you. But yeah, it would actually kind of get more and more out there. But do you see how I'm even incorrect in connecting them? Would these dots connect? They wouldn't even connect. They'd just be dots back and forth, back and forth. So yeah, it turns out the growth factor cannot be negative. Well, let's do one more just to make sure that I cover all my bases here. Check out this one. Y equals 5 times x to the 4th power. Does that follow the same pattern for an exponential? Is that an exponential pattern? Well, if it's an exponential pattern, you should be able to tell me what the growth factor is. What's the growth factor here?
X, right?
Yeah, x, and that don't make much sense. That doesn't make much sense for that growth factor to be unknown. So it turns out this is actually called a quartic. A quartic function. You don't have to know the name of that. You just got to know that it is not exponential. So just to kind of recap, to be exponential, where does your x have to be? It has to be outside, and doesn't it have to be an exponent? Your x has to be an exponent, and you're going to have a base that's a positive number. So it's kind of interesting. We're going to be practicing this a little bit for a while. Well, let's flip this over. Identify the function as linear or exponential. Then write a rule, which is just another way to say equation. Then write a rule or equation for the function. So number 1, how are you going to tell if it's linear or exponential?
If it's not multiplying, then it's linear. And
Okay.
if it's multiplying, then it's exponential.
So which one is number 1?
Yeah.
Exponential. Why?
It's multiplying by 5 divided.
Multiplying by 5. Timesing by 5. So it's exponential. And then we want to write it, the format is y equals ab to the x. What's our a? 1. A is our starting amount. It's 1. What's our b? The 5. The growth factor And then where does that x go? Up top. Number 2. Is that exponential as well? What are they doing each time? Multiplying by 2. Starting amount right there. So y equals starting amount was 5 times growth factor is 2. What's our exponent? An x. Next one. Ooh, we got some fraction-y goodness, don't we? Some fractions going on there. What's the pattern? Joey says multiplying by 2. Do you agree? Yeah, I do too. Multiplying by 2. So it's exponential. We need a starting point. What's the starting point? A fourth. Whoops, I wrote a half. A fourth. And our growth factor is 2, and the x is our exponent. Number 4, linear or exponential? Linear. Now, how do you suppose that? What's the pattern? Adding 2 each time? Yeah, that's linear. And remember, for linear, we do y equals mx plus b. What's our slope? 2. What's our b? -3. Now, in honesty, we should be just double checking and making sure these are going by 1 each time. If they're not going by 1, it would complicate what our slopes are and what our growth factors are. We would have to divide to find out what's going on. But you're only going to be given the basic ones for these types of problems. Number 5, what do you think? Exponential? Okay, so I'll let you guys fill them out, okay? That one's exponential. What do you think about number 6? Exponential as well? Exponential, so I'll let you guys fill those out, and I'll show you the answers here in a second. What about number 7? Exponential again?
By 11?
Nice. And what about 8? That one's linear. So yeah, go ahead and write these out. And yeah, try them out on your own. As I come around, if you have questions, let me know as you're filling those out. I'll project the answers here in a second. Any issues, any questions? Like your composition. It's a good color.
Yeah.
Do you like orange?
Yeah.
Yeah.
I like this fucking notebook.
Cool. Any questions, Lewis? You good? Yeah. Make sure to stick some Y's. Oh, go ahead. Yeah, no, I'm sorry. I'm interrupting. What else saying? You guys good? Yeah? All right. Well, I got, let's see here. I got those answers. What do you guys think? If you wrote it as -1 times 4 to the x, you're fine, aren't you?
Yeah.
You're totally fine. Just keep in mind that you could write it like this, but don't we recall that if there's no parentheses, don't you do the 4th power first and then put the negative? So it's just kind of something to think about. If your starting amount is 1, do you actually have to put the 1? Is multiplying by 1 going to change it? No, it's not. Same thing kind of there. And then on number 8, y equals 3x plus 4. Well, I'd like to do a little bit more for you, a little bit more, just in case, like on a standardized test, you see something like this, okay? Take a look. We'll add a number 9 here, if you got room. Do you got room?
Yeah.
Okay, so for 9, let's make a little box, table of values, and let's go 3, 4, 5, 6. At 3, you get 9. At 4, 27. 5, 81. And 6, 243. Well, you can still decide if it's linear or exponential, right? What do you guys think? Multiplying by 3? So it's exponential. We should be able to write an equation, but what's tricky about this? What's missing? Yeah, do we have the y-intercept? So what you could do is you could go backwards, right? You could go backwards and be like, 2 would be, what, be 3, right? And you could work your way backwards. You can totally do that. But what I want to show you is something that can help you with all sorts of functions. So what you could do is you could write this. You could go y is equal to, since you don't know the starting amount, just write what? A. Yeah. We don't know the starting amount, but do we know the growth factor? Now think about this. If we don't know A, is there a way that we could solve for it, given all these values?